Assalamu alaikum and welcome to the course on digital signal processing, having course code EEE 324, which consists of theory as well as the lab. And this is lecture number 1, and in this lecture we will discuss about the course contents, books you will be following for this course, and we will also overview some of the topics which are important for this, which you have already done in the course signals and systems, which will be used in this course also. So course description according to the catalog are review of signals and systems concepts, introduction to DSP theory and applications, signal transformation, sampling and quantization, discrete Fourier transform, fast Fourier transform, circular and circular convolution and methods of linear filtering, discrete time LTI system analysis in time and frequency domain, Z transform, digital filters, ideal and practical digital filters, finite impulse response filters, infinite impulse response filters, realization of digital filters, DSP algorithms and their implementation issues, DSP processor, DSP applications, etc. So the textbook for this course will be Discrete Time Signal Processing by Alan V. Oppenheim. Preferred is 5th or 6th edition. The reference books consist of Digital Signal Processing, A Practical Approach by Emmanuel C. Apicher, Digital Signal Processing by Saliwa Hanan, Advanced Digital Signal Processing by J.G. Prokes, Digital Signal Processing, a computer-based approach, McGraw-Hill, DSP First, a multimedia approach, Prentice Hall, but mainly we will these two books, that is Discrete Time Signal Processing by Alan V. Oppenheim and this one, the Digital Signal Processing, a Practical Approach by Emmanuel. So again, starting with the signals, you might have done these things in your course on signals in systems. So you know that signals and systems are ubiquitous to telecommunication, control, signal processing, power engineering, in fact all areas of the electrical engineering, but also some many other areas. Fundamental for all electrical engineering areas. So I hope you understand that engineers must model two distinct physical phenomena, that is physical systems and physical signals. Physical systems are modeled by mathematical equations, whereas physical systems are modeled by mathematical function, for example voltage applied to a speaker in radio, etc. So in nature, signal exists in different forms. Examples of the signal include electrical signal. In electrical signal mainly we have voltages in current in a circuit. Similarly, the acoustic signal, which are acoustic pressure such as sound wave over time. We also have mechanical signals such as velocity of a car over time, or acceleration, speeds, etc. Similarly, we have video signals such as intensity level of a pixel is a function of time and space variables. So formally, we can define a signal as a function of one or more variables that convey information on the nature of physical phenomena, right? So for a signal depending on one variable are called One-dimensional signals and those depending on more than one variable are called the multi-dimensional signals. For example, a speech signal is an example of one-dimensional signal, and grayscale image is an example of two-dimensional signals. Mathematically, signals are represented as function of independent variable. For example, we have f of t, so f of t signifies that f is function of the independent variable, which is time. Similarly, the independent variable can be frequency, such as this one. So in case of frequency, we use the uppercase letters. Similarly, for the case of the image, we have xy as independent variable, and it can be seen that the image intensity in this particular case is a function of two variables, which are x and y. So in this course, we'll be dealing with one independent variable. So we call them one-dimensional signal because we have only one independent variable, and the independent variable will be time or the frequency. For instance, in RC circuit, the signal may represent voltage across a capacitor or current flowing in the resistor. There is always associated system, right, such that it will for the generation of signal, and another system associated with the extraction of information from the signal. For example, sound is generated by vocal tract, lung, etc. The processing of speech signals usually relies on the use of the ears and auditory pathways in our brain. This system is biological in nature. A system is defined as an entity that manipulates one or more signals to accomplish a function, thereby yielding new signals. The input and output signals depends on applications of the system. For example, for speaker recognition system, the input is speech, the system is a computer, and the output is the identity of the speaker. So I think you have done all these things in detail in your course on signals and system. So basically we can say the signals in time domain can be classified into two categories, that is continuous time system and continuous time signal and discrete time signal. A signal is said to be a continuous time signal if the independent variable time is has continuous values. It is represented as x of t, where t is continuous. For example, sound wave, electrical signals such as voltage and current. Similarly, discrete time signals, we say a signal is said to be a discrete time signal if the independent variable time has discrete values, that a signal is defined only at discrete instant of time. It is represented as x of n, where n is an integer. A discrete time signal may be discrete time phenomena, or it may have been obtained from analog or continuous time signal x of t by sampling, such as x of n equals to x of t, and we have sampled the continuous time signal using the sampling time ts, where n is an integer and it is as values 0, plus minus 1, plus minus 2, plus minus 3, and so on. System is defined as anything that generates a signal, transmits a signal, receives a signal, or processes a signal. A system is made up of physical components, such as in case of electrical engineering we have resistors, capacitor, diodes, amplifiers, and so on, filters, etc. So it is made up of physical components, right? So system can be an electrical, or it can be mechanical, or it can be biological in nature, or it can be an algorithm that computes an output from the input signal. Software realization. So for a case of discrete time system, the input signals to the system are discrete and it produces some discrete output, right? So we have some representations of the system that are we can represent the discrete time system by block diagram, such as shown here. We have input signal, we have some discrete time system, and we have output signal. Similarly, we can also represent the discrete time system by mathematical equations, such as this one. We have output signal y of n and the input signal are theirs. So you can easily tell that the output is what the system is doing here. It is subtracting the present value of the system of the signal from its previous value, right? Similarly, we can represent a system by operations, such as y of n equals to h is an operator that performs some operation on the input signal to produce the output signal. So the next topic we are going to revise is the convolution sum, how to find the convolution sum. So to find the convolution sum, recall that we have to find the convolution sum, we must have the LTI system, and you recall that LTI basically is linear time invariant system, right? So the first thing is the system must be linear. So a system is said to be linear if it holds two properties, and these are the superposition and the scaling. So if a system holds both of these properties, we call it a linear system. And the next is time invariance. So if the system is also time invariant, that its characteristic does not change with time, then such a system is called time invariant, right? So if a system holds both of these, that is, it holds the property of superposition, scaling, and time invariance, then such a system is called LTI system. And for the case of LTI system, if we know the impulse response, right, so we can find the output of the system using the convolution sum. So you understand, impulse response is defined as the output of the system when the input is unit impulse, that is right. So you understand that we can define the impulse is defined as for example, impulse of n, right? So this is equal to 1 when its argument, which is n, is equal to 0, and it is 0 when its argument is not equal to 0, right? And you also know that we can represent the discrete time signal in terms of scaled and shifted impulses. So any signal, for example x of n, can be represented as summation k running from minus infinity up to infinity x of k impulse of n minus k, right? So we can represent, because we can represent any signal in terms of scale and shifted impulses, and we know that the system is LTI, so that means Knowing the impulse response, we can find the output of the system using the convolution sum. So we are going to calculate the equation for the discrete time convolution sum using the properties that are linearity and the time invariance. So convolution sum or convolution integral, they both are valid for the case when the LTI system, when the systems are linear and time invariant. So for example, we have a system represented by S. Okay, so when we give it input, it produces y for y, right? Y of n, because this is the discrete time system. So the simplest input is the impulse, right? So when the input is impulse, the output is called the impulse response. So because we know that the system is linear and it is also time invariant, so any shift in the input will result in the shift in the output, right? So it does not affect whether uh, the response is same, whether the input, right? By shifting the input, we have shift in the output, meaning to say it is a time invariant. Okay, the second property that is used is the uh, scaling property. That is, if input is scaled, right, so the output must also be scaled by the same version, right? So that means h of k basically represents the x of k basically represents the scaling. Okay, we give it impulse, the output is h of n. Because the system is time invariant, so shift in input results in shift in output. Also, we say the system is linear, so that means if I scale the input, right, this is your input, if I scale it by some factor of h of k, x of k, the output should also be scaled by the same amount. I hope you understand this. If this is clear to you, then it's very simple to do the uh, convolution sum. Okay, so these are the steps that are used for finding the convolution equation. Okay, so that means here we have scaled the input, so output should also be scaled by the same amount. And why it should be scaled by the same amount? Because the system is linear. Okay, then we use the superposition. The superposition is that if the input is, if the input, right, you have done this for the uh, linear system, so you understand that x1 of n, right, plus x2 of n, that means this is the superposition property, x2 of n, it will produce y of n such that y of n equals to y1 of n, right? This is equal to y1 of n plus y2 of n. Hope you understand that we have done this in detail while we were doing the uh, linearity property of the system. So if input is, right, originally you know that your input is impulse, right? So if you look at this one, this impulse is shifted version, right? So it shift in input produces shift in output, right? But they are same, right? Because if the system is time invariant, that means the uh, system has behavior that is independent of time. That means if you give it now something, it produces some output. If the same thing is given 2 days later, it will produce the same output. Why? Because the system is not time varying, right? So that means the shift in input produces the same shifted output. Okay, and uh, this is the scaling. Hope you understand. So if input is scaled, output is also scaled by the same amount, right? So if input is summation, then output is also the summation, right? That this thing we have done while doing the linearity property, right? So because uh, uh, so just recently you have done this, right? That we can represent any discrete time signal in terms of scaled and shifted impulses. So this is your x of n. Basically this is your x of n, and we have done derivation for this one, that any discrete time signal can be represented as scaled and shifted impulses. So x of n equals to this, and this is your y of n, right? So this is the equation of the discrete time convolution sum. So based on the steps mentioned in the previous slide for finding the convolution sum, let's have a numerical problem to find the uh, to use those steps and find the convolution sum, or find the output of the system using the convolution sum. Okay, so for example, we have a signal that is x of n, which is defined as shown here. So h of n consists of two non-zero samples. At index 0 it has the value 0.5, and at index 1 it has value of 2, and for all other values you can see the value of the input signal x of n is 0. Okay, so as far as the response is concerned, the impulse response is concerned, it has three non-zero samples, as can be seen here on in the figure on the top right, that at 0 it has amplitude of 1, at 1 it has amplitude of 1, at 2 it has amplitude of 1, and for all other values beyond 2, right, or beyond -1, these all values are 0. So it consists of only three non-zero samples, and all of them have equal amplitude. Now, based on the instructions on the previous slide, let's find the convolution sum, right? So the first step was to plot the signal, both response and the input signal, using by replacing the independent variable with k. So that means we have we can plot it here. So or straight away I just say, okay, I have already plotted using the n as independent variable. Now what I do is I just replace n with k, so it will become k, right? For you, you have to plot the signal again, right? And okay, and this n is replaced with k, so now you have h of k. Okay, and you have x of k, so you replace k with you replace n with k. So this is the first step. In the second step, you reflect any one of these signals, right? So I reflect the signal h of k, right? You can also reflect x of k to obtain x of minus k or h of minus k. So if I reflect it, uh, you can understand how we are going to achieve this operation of reflection. So you understand it's you've already done it while doing the operations on independent variable, right? So the reflected version of h of k can be obtained by placing a mirror here and looking into this side, right? So if I place a mirror here and look into this side, so this I will obtain this sample as it is here, and the samples samples which are at 1 and -2, they will be here, right? So let me plot. For example, this is the original, this is your origin. So let's take red color. Okay, so this is your uh, the sample at 0, and the sample at 1 will be placed here, that is now at -1, and similarly sample at 2 will be at position -2, and the for all other values they will be 0, right? Similarly, now again, if I put a mirror here, right, and if I look at in this direction, so you see all these values here, they will be uh, shown, or their image will be produced this side, because all these values, they are 0. So that means I will get something like this, right? And remember that this is your variable, which is k now. So this is what you obtain, that is h of minus k, right? So the next step was to add some negative value, right? So that we negative value n, a large negative value n, so that this signal which is at 0 is shifted to the leftmost. Okay, so let's do it. And okay, I use the same color, and okay, I say it's a bit different. So okay, so this is again the okay, so let me draw here. So okay, and this is the origin. Okay, so if I subtract a big value, if I add a big negative value with this, so originally this is at 0, so now it will become at n. Okay, n is a big negative value, so it's now n. This one is at -1, so this one will be at for example n minus 1. Okay, and then okay, so I have this, and this will be n minus 2, right? So this is 0. Okay, and this is, now we can write it like h of n minus k. Okay, so this is how you obtain h of minus k. So remember, we are using these steps that are mentioned in the previous slide. Okay, so you obtain this. Now the next is that you shift the signal, you multiply the corresponding values of the signal. So if I plot as the input signal again, right? So this is the input signal. For example, let me plot it here so that it is easy for you to understand what is basically happening. Okay, so this is the input signal. So at 0 it has value of 0.5. okay, this is value of 0.5. At 1 it has value of 2. Okay, so this is 1, and the value of the signal is 2, and this is your k axis. Okay, now we, as mentioned there, in the next step we multiply the two values, right? So you understand the signal is 0, here it is 0, here it is 0, that is 0 up to infinity, right? And similarly 0, 0, right, and 0, and this is up to infinity. Okay, so if I multiply the two signals, what will happen? Because this signal is 0 for all values, right? from -1 onwards. Now this signal is although non-zero, but when we multiply the two signal, you understand, if we multiply two quantity, if one of the quantities is 0, it will result into 0. So that means, because this is y of n, so we can say y of n equals to 0, right? And how long it will stay 0? It will stay 0 for all values of n when n is less than 0, right? So this is how you get zeros for right, because one of the signal is 0, then you take the next value of n. Okay, so basically you are moving the signal towards the, in this case, towards the right. Okay, so then you shift this signal right, and again you take the products, because step number 6, if you look at, then it says that we do it for all values of n. Okay, so now we are changing the value of n. Okay, you bring it closer towards this side, so again the product will result into 0 unless you reach at 0. So when n is near to 0, right, I mean when n is equal to, in fact, 0, in that case this signal is non-zero and this signal is non-zero, so the product will be non-zero. Okay, let me plot here again. So I hope this gives you understanding how what we are doing, right? So if I plot the signal again, so it means that so I have shifted the signal this way. Now if you look at this one, this is n, and if you see its index, so it's at position 0, right? So now if you look at this one, so again this sample multiplied with this, it will result to some non-zero values, but this point, right, multiplied by this will again result into 0. Again this point multiplied by this will again result into 0. So we do the product of sums, right? So we take the products of the corresponding values and then we sum them. Okay, so that means in this case now, because n is equal to 0, you understand this is the position of n, and if you see, this is position 0, this is position -1, this is position -2, and this is position -3, and so on, and this is 1, I hope you understand, right, 2 and 3 and so on. So that means when n is now it's 0, when n was here it was at a position of -1. So in that case the product of all were 0. So we can say that y of n equals to 0 when n is less than 0. So less than 0 means at -1, the corresponding products, right? You take the product of the corresponding values, that was 0 at -2, -3, -4, -5, and so on, and it stays 0 until n reaches 0. When n is 0, now we see that this one is non-zero and this is also non-zero, so their product will be non-zero, and summing them will result into non-zero value of the y. So when n equals to 0, you see that we can write y of 0 equals to what? Y of 0 equals to so you see 1 multiplied by 0.5 again, because if you move this side okay, if you move this side, you see all of these are 0, and again all of these are 0. Okay, so 0 into 0 will result into 0. Now at this point, okay, at this point it is 1, and this is sorry, this is 0.5 and this is 1, so 1 multiplied by 0.5, right? So it will result this one. Then again this sample is, right, this one is 0 and this is 1, So 1 multiplied by 0. Again, this sample is 1 and this is 0. So I write 1 multiplied by 0. So you see, 1 into 0, 0, 1 into 0, 0, 1 into 0 0.5, 0 0.5. So the value of the yn is equal to 0 0.5 when n equals to 0. So that's why I have mentioned here y of 0, right? Similarly, we can go for y of 1, right? So again, we will shift the signal. So now it is at 0. So if I shift it one more unit, then it will become y of n will have value of 1. So okay, I shift 1 unit further this signal. So now you see n corresponds to 1. So that means y of 1, right? N equals to 1. So because it's y of n, so y of 1. What happens at y of 1? You can see that now this signal has value of 1 and this has value of 2. So 1 multiplied by 2, which I mentioned here. Okay, this 1 into 2 plus this is 1 and this is 0 0.5. So 1 multiplied by 0 0.5, which is mentioned here again. Now if you look at this one, this is 0 and this is 1. So 1 multiplied by 0, so summing them will result into 2.5. So again, let's move one more step, and now n equals to 2. So for n equals to 2, we have the following, because right, so for n equals to 2, I will move the signal one unit, right? So here n corresponds to 1. So if I shift it one more, it will correspond to 2. So let's see. Okay, so shifting 1 unit again. Now n is at position 2, right? N minus 1 at 1 and n minus 2 at 0. So again, we do the same thing. We multiply the corresponding values and sum them, right? So if you look at this one, this is index 2. So here the signal is 0. So 0 multiplied by 1. You understand the response has constant amplitude of 1, right, for all these three samples. So we multiply 1 with 0. So this is what I have mentioned here. Then we multiply this one, okay, this one with 2. So 1 multiplied by 2, and again this one multiplied by, right? Now we multiply this one with 0 0.5, so which is mentioned here. So this will result into 2. 1 multiplied by 0 is 0, 1 multiplied by 2 is 2, 1 multiplied by 0 0.5 is 2, so that means it will result into 2.5 again. So again we will shift 1 unit this side, right? So now n is at 2. So after moving it to this, n will be at 3, n minus 1 will be at 3, right? And so on, right? So let me draw here. Okay. Okay, so by shifting the signal again 1 unit, so now you see that n is at index 3, right? N minus 1 is at 2 and n minus 2 is at index 1. So if you multiply the corresponding value, so this is 3, right? So at 3 the signal is 0, whereas the response is 1. So 1 into 0 will result into 0 as mentioned here, right? So 1 into 0. Again, for the second sample, this is at 2, and again at 2 the signal is 0. So 1 into 0 will again result into 0. At position 1, the response you can see is 1 and the signal has value of 2. So 1 multiplied by 2 will result into 2. Okay, so if I move one more position to the left, to the right, you will see that the non-zero overlap is 0. We don't have any non-zero overlap. What does non-zero overlap mean? Non-zero overlap means that both the response and the signal are non-zero. So we call them non-zero overlap. Okay, so shifting it one more position to the right results n equals to 4, and when n equals to 4, you see this is the fourth position. So here the response is 1, right? Response has value of 1, but input signal is 0, so 1 into 0 will result into 0. Again, at third position or third index, the response is 1, but the input signal is 0, so 1 into 0 will result into 0. Again, at second position, response is 1, but the input signal is 0, so that means the product is 0 and sum of products is also 0, so we can say y of 4 will be equal to 0, and it will stay 0 for all the remaining values. So I can write the generalized expression for y of n, and I can say that y of n equals to 0 when n is less than 0, okay, and it is equal to 0.5 when n is equal to 1. It is equal to 2.5, okay, when n equals to 2. It is equal to again 2.5 for n equals to 3. Is it 3? No, it's sorry, when n is less than 1, when n is less than 0, it is 0. It is 0 when n is, next step is, okay, that I made a mistake here, so let me clear it. Okay, so when n equals to 0, y of n equals to 0.5. When n equals to 1, it is 2.5. When n equals to 2, again it is 2.5. When n equals to 3, it is equal to 2. So 2 when n equals to 3, and 0 when n is equal to or greater than 0. So this is the expression for y of n, right? So I hope this gives you idea how we can use the graphical method to find the convolution integral, convolution sum. Okay, so the resulting signal y of n is plotted here. Okay, so you can see before 0, right, it is 0, and after 3 it is 0. So we can say when n is equal to or greater than, again it's wrong, when n is equal to or greater than 4. Okay, so for all values of n where it is equal to or greater than 4, this signal will, the output signal y of n will be 0. So the next thing we're going to consider are the properties of LTI system. I will go quickly through them. So the properties you are going to consider are the commutative property, right? So you understand commutative property is just the exchange of these, that is x of n convolved with h of n is same as h of n convolved with x of n. You understand convolution is an operation similar to what we have like multiplication, addition, subtraction, and so on. So you also know that addition also holds the property, addition and multiplication holds the property of commutative. So similar to addition and multiplication, convolution also holds this property. So that means if you convolve x of n with h of n, or if you convolve h of n with x of n, you get the same result. The other one is the distributive property. So x of n convolved with h1 of n plus h2 of n equals to x of n convolved with h1 of n plus x of n convolved with h2 of n. So combining these commutative and distributive properties, we can say that x1 of n plus x2 of n convolved with h of n equals to x1 of n convolved with h of n, and plus x2 of n convolved with h of n. Similarly, for the associative property, we can say x of n convolved with h1 of n convolved with h2 of n equals to x of n convolved with h1 of n and convolved with h2 of n. So here is a numerical example. I want you to go through it and solve it, right? The next is property with and without memory. So this is how we define, because you know that an LTI system is completely characterized by its impulse response. So by just knowing the impulse of response of the LTI system, we can tell whether a system is memoryless or it's with memory, it's a causal, non-causal, stable, unstable, and so on. So for a system, if the impulse response of the system is 0 for n is not equal to 0, then such a system is called as memoryless system. If this condition doesn't hold, then we say a system is with memory, right? So all these things you have done in your signal and system course. So I will just go quickly through them. If you have any confusion, you can ask me in the live session. So I think that's all for today. Allah Hafiz.